Dr. M. Subbaya is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on statistics interdisciplinary. Being interested in active research program and mathematical or statistical modeling, he has knowledge in operating various softwares on statistical tools and on technical computing. Having 16 years of teaching experience, he has published papers in 8 national and international journals, and has also presented papers in 10 national and international conferences.
Welcome to the UGC lecture series on mathematical sciences. Multiple and partial correlations will be the point of discussion today. As far as correlation is concerned, when we have more than one variable, start from a pair of variables, it may be interested to find out how much they are related. The degree of relationship is first of all to be calculated in a numerical form whenever there is a reasonable relation exists between those two identified variables. So, theoretically or some hypothetical relation would exist between more than one variable starts from a pair. So, we may have to understand what is the degree of relationship between these two variables. Such analysis, what we call it as normally correlation, can be extended to a set of more than 2. While doing so, we will have 2 aspects to consider. Number 1, multiple correlation. So, the term is quite straightforward in both the cases, multiple correlation and partial correlation. So, the word multiple is a straightforward meaning that we would like to consider more than 2, of course, more than 2. So, as far as partial is concerned, it is quite very similar as far as the number of variables are concerned, but we would like to suppress certain variables. It is possible because in some cases we may not necessarily involve all the variables. For example, we may have to understand how the amount of rainfall could be affected or how much it is related with many scientific factors like atmospheric pressure or the humidity, sea surface temperature and so on and so forth. While considering such a pool of variables, sometime the humidity may be considered as a constant, or I just to consider or suppress for a time being. We may not include it in the impact of analysis. So, we consider only a partial list of variables so that the effect could be understood as a degree of relation. So, there would be 2 kind of correlations we will discuss here based on what is the way to calculate and few straightforward examples, so that we can understand the formulas whichever is used to calculate multiple and partial correlation. We would like to insist that as far as calculations are concerned, the formulas are quite straightforward, but still a simple knowledge of matrix manipulation, matrix algebra would be helpful to generalize the formula quite straightforward. Anyway, that is not so compulsive, but the formulas are interpretable or written in matrix notations also. Anyway, the definition of multiple correlation goes like this: whenever there is more than 2 variables are involved, we would like to find out the joint effect upon a variable not included in that group. So, I would like to have 3, for example, let us symbolize x1, x2, x3 for simplicity. I may find out the effect x1, a joint effect of x2 and x3 on x1, and similarly for the other permutations. So, 3 permutations with 3 variables, of course. So, 1, 2 and 1 and 2 with 3 and etcetera. As I mentioned of one situation here, I have another example collected from this material. Playing computer games may be associated with social isolation, lowered self esteem and aggression. So, these are all certain psychological variables, whether one we can treat and then find out the joint effect of other. So, the situations are many in fact in practical. I just provide one example here where you could understand or where you could realize the need for such a joint effect and joint effect of 2 on the third. Of course, the number can be extended based on the study, based on the problem. So, for simplicity I try to explain initially with a trivariate relationship, because 2 is too small where we have only a linear or a non-linear correlation, where we are going for only 2 variables. Therefore, essentially for multiple correlation, let us start with a 3 variable case, and we can name them as x 1, x 2, x 3 and let them have n observations. So, this is a symbol or 1 dot 2 3. I think the symbols are not so complex, because what the definition would like to say is joint effect in the upon the other variable which is not in that group. So, you could easily understand that 2 and 3 are grouped, obviously 1 is left over. So, joint effect of 2 and 3 on 1 will be studied. So, the simple correlation coefficient between x 1 and the joint effect of x 2 and x 3 on x 1. So, the symbols could be easily generalizable or extended at least to a 3 variable case per se, or 2 dot 1 3 etc. So, that is how this relation could be remembered or it could be understood basically. So, the formulas are this capital R, we try to stick to this multiple correlation, because there is another correlation where we have symbol with small r, which is nothing but the simple correlation between tth and s variable. So, what I symbolize here as r suffix ts to refer 1 2 1 3 and 2 3. Of course, this is a 3 2 is not necessary, because correlation between x 2 and x 3 is quite similar or same when you swap the variables. Therefore, that is not a big problem. In fact, that is not necessary. So, r 2 3 is enough. So, we will calculate the simple correlation basically, which is nothing but Karl Pearson's formula. So, symbol wise we prefer capital R for multiple correlation and small r for simple correlation between the pairs. So, the formula goes like this. One way to remember, as I mentioned in the beginning of the session, we would like to write those formulas in a matrix form, so that it can be easily remembered. That is point number 1. Second is, matrix form will be useful to generalize the case for more than 3 variables. So, here we just observe the formula for 3 variables. Therefore, the other way to write with matrix equations will help you to generalize the cases. That is what here I would like to start from. So, this simple correlation is nothing but the calculation from Karl Pearson formula, which we will go through with the examples basically. Therefore, the essential prerequisite will be the knowledge of Karl Pearson's correlation formula, how to find out. Anyway, the formula can be rearranged or represented in a matrix form, which is a 3 by 3. The reason is simple, that we have 3 variables and there will be 3 combinations of correlations, simple correlation of course, 1 2, 1 3 and 2 3, that is well placed in the first row second column, first row third column and second row third column. This is below diagonal will be the same quantity. In fact, this has to be 2 1, but I deliberately put as 1 2, because these two are essentially the same. So, R 1 2 or R 2 1 based on the matrix notation, we do not distinguish heavily on that. So, these two are quite same. Similarly, R 3 1 third row first column is same as this one, therefore, we go by that. So, anyway it is in matrix language, it is a symmetric matrix, though it is not so strictly known about all those things. We just remember how this matrix is formed. Diagonals are 1, then position wise, then because of symmetricity or the pairwise relation R 1 2 is same as R 2 1, this determinant can be calculated. So, omega is to calculate this formula numerator. Then I will be calculating something more than that from this omega W 1 1. A quick observation is, numerator we have a determinant form, then the denominator is also important, that we calculate using one more determinant termed as omega 11. So, the formula for R 1 2 3 will be calculated in the numerator omega, which we have the determinant 3 by 3 order. From that you can derive a submatrix and whose determinant can be calculated, what generally we call it as cofactor of the given element. So, easily we could understand we are calculating it for 1 1 first row first column. So, what it actually means, suppose I take this is the first row first column element, remove the row 1 and remove the column 1, rest of the thing you will get obviously a 2 by 2, calculate the determinant what we call it as omega 1 1. So, generally or this particular case omega 1 1 is a cofactor of the element in first row first column that will be obtained from omega of course by removing first row and first column. So, that is given by this index. So, this representation could be encouraged because it is easy to remember compared to this long expression how it works. So, working rule as far as this multiple correlation is concerned, of course, with the 3 variables what we refer here, we calculate based on a determinant which is calculated from Karl Pearson's correlation coefficient between the 3 pairs 1 and 2, 1 and 3 and 2 and 3. By mentioning this order, I just visualize how to write my determinant first row second column, first row third column and second row third column, then rest of my elements in the below of the diagonal of omega will be exactly the same. So, with this idea I just once again flash this omega for your remembrance, so that this comparatively less easier to remember, but we prefer this kind of notation so that you just calculate the determinant of a 3 by 3 matrix. From that, one more easier way to remember the denominator is not to trouble much. What variable is not in the pool 1, that will be collected here as a cofactor of first row and first column. So, in general for a trivariate case, 3 variate case I j k, I refer I is not in the pool, j and k were the pool. So, that the joint effect of j and kth variable on I will be studied by this form. Omega will not change of course, but what is the denominator omega I which will be obtained from the matrix omega by removing ith row and ith column. So, that is what in the special case I refer and the general formula. Therefore, as far as 3 variable is concerned, in fact, this formulation can be easily remembered, understood to generalize it for any number of variables involved in that. In fact, these formulas are quite reasonable to apply, of course, when you have more than 2 variables in the given problem. In fact, this is the general formula for any matrix. So, we are supposed to calculate 3, if we have 3 variables, then we have 3 C 2. So, what I mean by that is you have to select 2 variables at a time from 3 variables. Obviously, you will have a combination 3 C 2, therefore, you will have 3. So, generally speaking the exercise would be much lengthier. So, now if we look at the problem as far as the multiple correlation is concerned, of course, we have to specify what kind of correlation we are interested. By looking at a trivariate problem, we may be sometime require a pairwise correlation alone that will handle 3 different pairs, and sometime we may be interested in calculating the partial correlation or sometime the multiple correlation. Anyway, here I deliberately include the word compute the multiple correlation of x on y and y and z. Of course, the way to read is to be cautious. Correlation of x on y and z. So, the joint effect we refer to y and z, second and third variable. So, that I maintain the way the formulas are discussed just now. Of course, not much necessary in a general setup. So, the way the formulas are to be applied is based on the number of variables, and what we have observed so far is how to calculate the coefficient of multiple correlation when many variables are pooled and one variable is left over. So, we call it as joint effect of those variables on the deleted variable, and we have observed a case for 3 variables and then generalizing it to any number of variables. Let us see the little numerical example after a short break. Welcome back after the break. So, just now we observed a formula for finding the multiple correlation in a simple condensed form with a matrix of omega and cofactor or submatrix. So, this omega can be generalized to n variables of course, though we have listed only for 3 by 3. So, that we can quickly get into the calculation now. Look at the way the table is required. I make 3 different color combinations just to show you that the left panel 3 columns are given data, nothing more than that. Then the rest of the things to be calculated, one set calculates square of the given variable, the next 3 calculates the cross product of 3 variables, of course 3 C2, x y, x z and y z. In a general notation what we have 1 2, 1 3 and 2 3, whatever the order we try to do. And the last row which is after the line here, they all represent the summation of the respective columns, just we add all those things. So, all these computations are quite direct if we use any calculating machine, maybe a computer or a calculator, whatever the case may be. Anyway, the computations are not far away, they are so difficult even for manual, but time consumption, that is all. Anyway, the Carl-Pearson's correlation formula, which we are calculating by the computational form x y, the cross product, and then summation of x, summation of y, then x square, summation of x the whole square, similarly the quantity for y. All of them are available in the previous slide. If you look at, for example, summation of x square and summation of x the whole square. So, fourth column and the first column are necessary. Similarly, y square and y, and then cross product we have 3 plus 3 6, seventh column here 285 has to be plugged in, and that is what happened here. So, I just plug all those required value from this formulation to from this table. So, that I get this particular expression and I get a Carl-Pearson coefficient of correlation as minus 0.2121. In a similar way, I just calculated R13 and R23. So, they are all based on the single table computation x square, y square, z square and then cross products. Now, we are ready with Carl-Pearson's correlation between the 3 pairs of variables. Remember to plug the determinant here, the diagonals are 1, R12, then R13, then R23, all of them are plugged here, and remember the symmetricity here. So, that I plug here 2 1, that means the position, third row first column, and first row third column will be the same, similarly these 2. So, I have to calculate the determinant, then similarly I have to calculate W11. So, which is the cofactor of first row first column. So, that we will calculate here as removing the first row and first column. So, that you will get 1 minus 0.0393 and this one. Similarly, I calculated omega and omega 22, removing second row and second column 1.3693, then this third row first column, third row third column. Computations are quite straightforward, AD minus BC square. Similarly, omega 33. So, all these computations are essentially needed to calculate all partial, I mean all multiple correlation, and now we compute omega also to calculate the multiple correlations. Omega is calculated as the determinant for the matrix, which we have 0.8076. I just want to recall here, because this is computed little earlier in our slide 3 3, 2 2, 1 1, and all of them are recalled here cautiously for submatrix. Now, I just explained the quantity what it refers to. So, the computations are omega by omega 11, 22 and 33. So, the numerator will be the omega in all the 3 cases, deleted variable is 1, the grouped variables are 2 and 3. Similarly, 1 and 3 are grouped, effect on 1 and 3 is studied as far as 2 is concerned. Similarly, the joint effect of 1 and 2 on 3 is studied. So, all of them refer here as a correlation value. So, the interpretation is quite similar to simple correlation. We would like to have the strength more or less to 1, so that we will try to have a thick correlation. That means, a strong relationship between the given set of variables. Anyway, the idea is different because here it is joint effect, but the numerical interpretation is somewhat similar to the simple correlation. Therefore, once we have all this computation from the determinant and cofactor, we are able to calculate the multiple correlation of anything. So, naturally, as you observed from the simple 3 variable cases, similar pairwise computation can be extended to more than 3 also. Only thing is the computational aspect will be little extensive. Even if you take 4 variables and 2 variables at a time, if you consider 3. So, the way in which we make the block of a set of variables with the other one, the number of computation will also become more and more. Next, in our aspect of correlation, as I started in this discussion, the second part of the correlation analysis will go with partial correlation. Situations are quite similar, but here again we have 2 variables. Now, the interest is study the relationship between 2 variables only. So, what will happen to the third variable? We try to eliminate its effect. So, we will not get into the picture, that is what I said in the beginning of this session. Sometime the humidity or sometime this sea surface temperature would remain constant. So, the effect need not be pulled in unnecessarily for that particular time of computing the correlation. So, that quantity will remain constant. So, that will not have any impact as far as the period we could say for this particular example, the period of computation is concerned, maybe a day or a week, whatever may be. So, it depends on the situation. So, I just take eliminate mathematically the effect of other variables on these 2 variables. So, the notation is slightly different. Compare with multiple correlation where 2 are joint and 1 is given, but now what is to be eliminated. So, the right side of the dot speaks the way in which the computations are being done. So, earlier we have the right side of the dot where the joint effect is being done over 1, but now look at the way the symbols are given. The right side of the dot would be which variable we try to eliminate. Okay. So, R 1 2 will be considered by eliminating the effect of 3. That does not mean that we are throwing the data from the calculation, that is not the way. In fact, if we do that case, then the total effect will be removed. In fact, the bundle will, I mean the modeling bundle will not contain the relevant dependent variables sometime. Therefore, we are not throwing it away basically, but mathematically we try to eliminate the effect of third variable. Once again, the formulas are quite straightforward, calculated from the Carl Pearson's correlation. So, now once again I would like to say how those quantities are to be calculated. 1 2 effect is needed. So, third is dropped or eliminated mathematically. So, I am remember C 1 3 and C 2 3 calculated from the respective Carl Pearson calculation R 1 3 and R 2 3. Anyway, the formula says square of it, but my emphasis would be to calculate the required Carl Pearson correlation 1 3 and 2 3. This formula is also having an equivalent form like the previous case omega. So, the same symbol is going to be applied, but the denominator is slightly different. Anyway, these notations are not new when we compare from multiple correlation aspect. Omega 1 1 and omega 2 2 are 2 cofactor matrix, cofactor of the element at first row first column and second row second column. Hope you could understand how the denominator to be remembered. Which variable we try to calculate? We suppress third, we included 1 and 2, therefore, the denominator is the respective omega 1 1 and omega 2 2. So, that means you are going to find out the cofactor of first row first column and second row second column. The combinations are quite straightforward when we change this order. For example, 1 3.2 will have omega 1 1 omega 3 3. The notations are not new as far as this discussion is concerned, because we already involved with those kind of things. it is obtained from the original 3 by 3 determinant by removing kth row and rth column. So, as I mentioned, the formula can be remembered this simpler way 1 3, the denominator has omega 3 3, and similarly 2 3, the denominator has 2 3 3 3, and these are all cofactors. So, cofactor of second row third column, second row second column, third row third column. So, quite easy to generalize with the omega is extended to, as I told you already, first row second column, first row third column, so on and so forth, first row nth column. Look at the elements above the main diagonal, rest of them are systematically very similar. So, the matrix can be constructed very simply and directly by looking at the elements above the main diagonal. Main diagonals are filled by 1 and above diagonal we can remember the position. Suppose I have first row fourth or 1 4 means I have to calculate Carl-Pearson correlation between first row, first variable and fourth variable in the list. Similarly, we can do it for n cross n determinant. And now, you will all understand what I mean by this dot, do not mislead by this is for continuity. Anyway, the dot refer here 1 and 2 are considered, rest of the n minus 2 variables are not considered for the analysis, which we refer eliminated mathematically, not from the group of calculation, that is not the intention. Anyway, the formula is very similar whether you have a 3 variable or n variable, the formula does not change because you are going to consider only 1 and 2. That is the ease of generalization. If you look at the way the formulas are written in a matrix form, that will teach you how to write for any number of variables in the given pool of problem or given set of variables. Therefore, the matrix notation is comfortable and of course, computationally quite direct. Now, an example with 3 variables, I try to calculate partial correlation of x y. So, obviously, z is suppressed. Anyway, the computation is exactly similar to the tabular form of multiple correlation. So, I do not have to explain one more time here. Anyway, the table is given in a 3 panel format to understand the first 3 columns in the left pan is the given data, and the middle pan is calculating the square of each column, and the last pan which has 3 columns calculates the cross product for Carl-Pearson's correlation. Similar to the previous table, we have the last row calculated as the summation of each column. Then I have Carl-Pearson's correlation, which is again the similar form, and we plug everything to get R 1 2, R 1 3, R 2 3, which is computed from this. So, all these calculations are, again I would like to say that it is little computer intensive or calculator intensive. Manually it is possible, only thing is the time consuming and little bit probably error prone. I am not say that we are always, but we may. So, I calculate all the relevant calculations omega 1 1, omega 2 2, omega 1 2, because that is what I require here for partial correlation, and then I plug the respective quantity omega 1 2 289 for the square, omega 1 1, omega 2 2, which we calculated earlier. Here they are all plugged straight away in this formula. Computing this, we get the answer for partial correlation of 1 and 2, eliminate mathematically the effect of third variable. A word of caution here, W 1 2 is having a negative sign. Anyway, when you square it, that sign will be removed, but while you take the square root, naturally you will have plus or minus so and so. Which value to be applied or which value to be considered, it is dependent on the sign of W 1 2. So, naturally this will give plus or minus 3185. I have to consider negative sign because I have sign minus for W 1 2. I just recall quickly that this is minus, that is why I have a minus here. Have a caution to put sign of this correlation. In a concluding summary, we just observe how to calculate the multiple and partial correlation based on the Carl-Pearson's coefficient for simple correlation, and then understand how to write the formulas for multiple as well as partial in a simple matrix form, where we depend on the determinant calculation as well as cofactor by removing the specific row and column. So that the formulas for multiple and partial correlation can be extended to any number of variables, though our discussion is very much limited to 3 variable case. For quicker calculations, I refer, and of course, I consider few problems here from this text. You are encouraged to look at more problems of similar texts. Still, I provide with 1 and 2 problems, so that you could understand the way in which it is calculated. So, once again I would like to remind how to remember the formula from the matrix form, and little bit computational intensive, that is the word I would like to emphasize. So, we have to be careful in doing all the computations, knowing the boundaries of correlations, so that we will not exceed while we computing, and we have to have a careful computation altogether in the computation of multiple, partial, or even if it is simple correlation. Thank you for joining this particular session.